Hi, today we're going to go over Chapter 3, our chapter on the innate immunity, which is the immunity that you happen to be born with. So the immunity that you have as soon as you're born can attack any pathogen as it comes in your body. Now, not any pathogen. It has to have certain receptors on it for your innate immune system to be able to attack it. But in general, it is what you have when you are first born, okay? It is composed of two systems that work to promote phagocytosis. When you think innate immune system, think phagocytosis. You may remember that big Pac-Man type character that I drew on the board that was a big phagocyte eating the bacteria with the certain antigens and toll-like receptors on it. That is what I'm talking about. Phagocytosis is the process of destroying a foreign organism by ingesting it. The first one is the external defense system. These are the anatomical barriers designed to keep microorganisms from entering the body. This would be mucous membranes, unbroken skin, tears, saliva, things like that. The internal defense system includes those cellular responses that recognize those specific molecular components of pathogens, like the neutrophils that are able to phagocytize things. Again, this is just where some of those external barriers are, okay? Lysozyme is one that I want to point out because we haven't talked about that in great detail. That is found in tears and saliva, which acts as a defense. It's an enzyme that can help destroy foreign organisms. You also have your stomach and gastric acid, which isn't something that we've talked about a whole lot. We knew about our skin and the mucous membranes. The skin has the epidermis and the dermis layers. They each have a different type of role in this. The epidermis has tightly packed epithelial cells that are coated in keratin. That keratin does help keep things from getting in. The dermis is the connective tissue with the blood vessels, hair follicles, sebaceous glands, sweat glands, and WBCs, which is another layer that is very difficult to get through. Some other things that the skin has is a lactic acid and fatty acids that maintain the skin at a pH of 5.6. That is sort of a pH that bacteria don't like. They usually like, a pH that's a little bit higher than that, maybe 7, somewhere in there. We also have psoriasin, which is a small protein produced by skin cells that has antibacterial effects. In the respiratory tract, mucus secretions block bacteria from adhering to epithelial cells. Coughing and sneezing moves the pathogens out of the tract as well. If you think of at the time of recording of this, it is, minus 50 wind chills outside. It's very dry, very, very dry. And you're going to find that a lot of people's mucous membranes are drying out from this dryness. And what happens then, it creates an extra area for pathogens to get in. So I'll check me if I'm right here, but usually after a big dry spell when it's cold like this, we see a big influx of people getting sick. And I think a lot of that is from having these dried up, sometimes even cracked mucous membranes. If you fly in an airplane, very, very dry, very, very dry. So people not only just being in a close proximity with all the people coughing and sneezing on the airplane, but the fact that your mucous membranes are a little bit drier than they would normally be allows for more pathogens to come, into your body, unfortunately. Urine helps remove potential pathogens from the genitourinary tract as well. It helps flush pathogens away. So people that get recurrent urinary tract infections, they say to drink a lot of water and maybe a lot of cranberry juice, which will help bring some of the pH down to prohibit some of that growth. The digestive tract also has hydrochloric acid that keeps pH as low as 1. This prohibits microorganisms from growing. So pH being very, very low, that's like really strong acid. We also have normal flora. Okay, normal flora helps keep the bad pathogens away. Next, we'll quickly discuss the internal defense system. With this, we have to recognize that pathogen recognition receptors are what these cells are looking for. So, bacteria have certain molecular patterns on them that these phagocytes are able to recognize and eat. Acute phase reactants help promote the inflammation in the area. Okay, so once those are present, it draws more cells to the area. We know what phagocytosis is by now. I think we've pretty much beaten you to death with that one. And then we also have those natural killer cells that are able to go in and just destroy any foreign organism, which is a type of a T cell, which, is kind of strange because we don't consider them to be phagocytes, but they do have that role as well. These pathogen recognition receptors that I keep referring to recognize molecules as the unique to infectious organisms. We find these on macrophages, dendritic cells, neutrophils, eosinophils, monocytes, mast cells, T cells, and epithelial cells. They're encoded by the host DNA to sense extracellular infection. They recognize the pathogen-associated molecular patterns on microorganisms, which make them enticing to that phagocyte. When they're bound to a pathogen, they do activate the phagocytic cells to destroy them. Here are some examples. Toll-like receptors. There are 10 types found in humans, and some are on cell surfaces, some are in cytoplasm. Okay, here's a gram-positive bacteria with some examples. Don't have to memorize those. It's just showing that they do sit on the cell surface. Some of the characteristics of those toll-like receptors, they're glycoproteins that bind to certain substances. They activate cytokines and chemokine production and other processes to enhance phagocytosis. Some of the cells release these cytokines or chemokine chemicals out into the bloodstream. And what those do, and they sound like what they do, cytokine gets the cells, chemokines are chemicals that draw them in. So once those are released from the cells into the general area of inflammation, it calls in all of those other cells to come and help. And it can destroy most pathogens in humans that are exposed before the disease sets in, as long as the disease isn't too overwhelming. Next, we'll talk about some of the acute phase reactants. These are soluble factors found in serum. They increase rapidly in response to infection, injury, or tissue trauma. Now, these are not very specific. They're sensitive, but not specific. So if you were to get in a car accident and have crushing injuries, you would have an increase in acute phase reactants. If you have an overwhelming septic infection, you're going to have an increase of acute phase reactants. So a doctor drawing an acute phase reactant type test on a patient would not diagnose them with something or the other. It would just tell them the extent of the injury or tissue trauma. It will be increased in a number of things. It also facilitates contact between microbes and phagocytic cells. Okay, think of it as the A1 steak sauce, kind of like opsinogens that we'll talk about. Okay, it makes things more delicious. It mops up and recycles important proteins after phagocytosis as well. So here's a chart that I'll share with you and some important things that you need to know. As you move through the MLT program, you're going to come across these many times, if not here, also in clinical chemistry. So C-reactive protein, that's one that is increased in general inflammation. Like I said, I could kick you in the shin, you could get in an accident, you could have an overwhelming infection, and this one will be increased. Its function is to increase opsonization and complement activation. So it will help draw in some of those factors needed for that. Serum amyloid A, I have a little blurb down here on that one. That one activates monocytes and macrophages, but we see a 1,000-fold increase in response to an infection or injury. So this one really increases a lot, especially in bacterial, more in bacterial than viral infections. And what happens is they can develop this amyloidosis in tissues, which is kind of like a scar tissue forming from this. And it can cause damage to things like the kidneys. Alpha-1 antitrypsin is a protease inhibitor. We see that one increased with emphysema sometimes. Or I should say, not increased, sorry. People with emphysema, it could be due to a alpha-1 antitrypsin type of deficiency. Fibrinogen, that's considered an acute phase reactant. It's involved in clot formation, where the platelets come in and it needs that fibrinogen to make that clot. We learned about that in coag last week. Haptoglobin binds hemoglobin. Okay, so after red cells are destroyed, you don't want to pee out all of your hemoglobin, so haptoglobin grabs onto it so it's not excreted by the kidneys. Ceruloplasmin binds copper and oxidizes iron and complements C3. That one's a really important important for opsonization. You've heard me talk about opsinogens and opsonization quite a bit in the last probably week, and are probably not really sure what that means. But complement C3 coats the surface of the cell. It's kind of like putting salt and pepper on a cell to make it more delicious. That's what it does, so that when the phagocytes come along, they're like, oh, this guy is yummy. Okay, so that's what opsonization does. So with the process of inflammation, sorry, the body's overall reaction to injury or invasion by an infectious agent will cause these things to happen. It's going to cause redness, which we refer to as erythema. It's going to cause swelling or edema. It's going to cause heat to the area and even some pain. Okay, if you've ever had some type of an infection in a wound or a cut where it starts to turn red and swollen and it hurts, there's heat there, that would be inflammation. Here's what happens during that process. I always love a good picture. So here, the resident macrophages and mast cells at the site of infection release chemokines that cause vasodilation and induce selectins. These selectins here, number 2, see them kind of stuck to the side, loosely bind circulating leukocytes and cause them to roll along the vascular wall. The chemokine-induced integrins on the leukocytes bind firmly to the endothelial cells, as you can see in 3. The integrins enable the leukocytes to crawl between the endothelial cells. This process is called diapedesis, okay, as it squeezes through. The leukocytes then follow the chemokine concentration gradient to the site of infection. You can kind of see him squeezing through, and now he's in the tissues, and he's going to work his way, kind of like a worm through the dirt, to get to the site of infection. This is called chemotaxis. Think of taxis. It looks like it's got the word taxi in it, and you transport yourself in a taxi. That's the process of moving to the site of infection because of a chemical. All right, the cells that are most involved in phagocytosis are neutrophils, monocytes, macrophages, and dendritic cells. This whole process is enhanced by CRP, which I mentioned in the slide before. But you do need to be a little bit familiar with the steps of phagocytosis. This book provides some fantastic pictures for this. I love it. So the first step here is adherence. This is the physical contact between the phagocytic cell and the microorganism, aided by the opsonins, which is the C3. Then we have engulfment. Okay, starting to engulf through the cytoplasm into the microorganism. Then it becomes capsuled in a phagosome. Okay, so it's completely surrounded. And then in 4, we have granule contact. You see these granules coming in, and those lysosomal granules contact and fuse with that phagosome. Then step 5, there's a phagolysosome. So we had the phagosome, the lysosomal contents come in. Then we have the phagolysosome, and this is where the lysosomes, everything is bound together in one space. Once those are in there, it starts to digest the foreign organism. At the end, it's excreted. Okay, so the contents of the phagolysosome are expelled outside by exotoxins. Oops, sorry about that. Okay, so that's the little process of phagocytosis of what happens inside the cell. The next one that we have are natural killer cells. This is the first line of defense against cells that are usually virally infected, okay, because viruses replicate inside the cells. So if you have a white cell, a healthy, happy white cell, viruses put themselves inside those cells and replicate, and then they burst open, and then you've got lots and lots and lots of viruses everywhere. They're a little trickier to attack, because normally your body doesn't like to attack its own cells. So your body has to recognize the fact that, okay, there is a virus inside that white cell, I need to attack it. It's a little more challenging, which is why viruses are a little bit tricky. Cells are infected with other intracellular pathogens or cells that are, or tumor cells as well. It can recognize any damaged cell and can eliminate it without prior exposure to it. So it gives the immune system time to activate the adaptive response to specific T and B cells. So sometimes there's things in there that shouldn't be there, and if your body had to wait for the adaptive immune system to come in, it would be too late and we'd all get really sick and die. That'd be unfortunate, right? So these are stimulated by exposure to cytokines, and when activated, they produce additional cytokines and colony-stimulating factors. These influence the innate and adaptive immunity to come in and help out. So they're very, very powerful. And as you can see in this video here, there's cytotoxic T cells attacking cancer cells. It's something that they're trying to do, or have been trying to do for many years, is figure out how they can create these cytotoxic T cells that are very specific to cancer cells to promote, your body to fight off these cancers yourself, rather than using very strong, chemicals such as, why is this not coming to me? Chemo. People go for chemo treatments, okay? That's very hard on the body. Using your body's own immune system to fight off cancer, well, that wouldn't be very hard on the body because the body's used to it, right? So here's the mechanism of cytotoxicity. Regular cells can inhibit the natural killer as well. So if a natural killer comes along and sees a target cell and it recognizes it as being a normal cell, it doesn't kill it, right? Because you don't want your cells to kill your own. Now, if it is a virally infected target cell, you can see the little virus here, it will destroy it, and the process of apoptosis will happen. That is cell death. Apoptosis is cell death, okay? We have an antibody-coated target cell here too, which will also cause apoptosis. So this natural killer cell can just attach to the cell itself or an antibody. So it can do a number of things in a number of ways. So that completes our section on the natural immune system, or the innate immune system. The next chapter is going to be on the adaptive part. So after we've been exposed to these pathogens, what happens next?